We have mutual inductance and self-inductance on the docket for this video. Starting with mutual inductance, if we have a couple of loops, they can induce currents in each other. Essentially, before, when we looked at induced currents, we were just looking at a single element in a magnetic field, but we didn't really talk about where that magnetic field came from. Now we're going to say, well, if I have one loop producing the magnetic field that will induce a current in the other loop, how are those things related? So I can start out by saying the EMF in loop 2 over here will follow the same equation we had before, which is going to be the number of loops in the coil, and I'm going to use subscripts to distinguish between quantities that apply to coil 1 and quantities that apply to coil 2. Times the rate of change of flux, and here we want the flux through coil 2 due to coil 1. So I'm going to do 2, 1, and then we have the time derivative of that. Now if we think about how this magnetic field is produced, we can say that the total flux through coil 2 is the flux through a single coil in coil 2, or a single loop, sorry. We'll call the whole thing, the whole bunch of loops, a coil, and a single loop we will call a loop. So it's going to be the flux through a single loop times the number of loops. We're going to have N2 here. That is going to be proportional to the current in coil 1. And if we want to make this an equality, we can say we need a coefficient in here, and we're going to use M, and we're going to call this M21 for now, because the M stands for mutual inductance. And so we're going to say that's the mutual inductance on 2 due to coil 1. And it still equals this over here. So if I rearrange this and I solve for my flux, I'm going to get flux 21, kind of missed my circle there, equals I1, let's see, where did I go? M21 over N2. And if I plug that in here, and then I can pull out the M and the N because they're constant. So I'm going to get N2, I'm going to get an M21, another N2 over here, and I'm just left with the current in coil number 1 in my derivative over here. These N's go away, and I get a nice expression for the EMF due to the changing current in coil 1, the EMF in coil 2. Alright. Now we can reverse all of that logic, and we can get an expression for the EMF in coil 1 if we were looking at the current in coil 2. So we just switch all of our subscripts here, right? So that would depend on the current in coil 2, the rate of change of the current. So we have this. And if I look at this mutual inductance here, if I rearrange that, I'm going to say that the mutual inductance, M21, is going to equal the flux times the number of coils over the current in the other loop. So this is a good expression here as well. This quantity of mutual inductance has units of henries, and a henry is a volt second per amp, which is also equivalent to an ohm second. You can also look at this situation here, and you could see that, well, flux is Tesla meters squared, so this is also equivalent to 1 Tesla meters squared over amps. So anyway, we just call them henries. Now M12, again, just swapping all of our subscripts here, so 1, 2, N1 over I2. And it turns out that M12, we're not going to prove this here, but it can be shown that these two things are equal. So typically we just call it M, and then we get rid of the subscripts because there's the same mutual inductance going either way, essentially. Okay. Now let's look at a situation. By the way, this is kind of a general expression for the mutual inductance. You can find it either doing this or doing this. These are general expressions for the EMF induced due to mutual inductance. But now we're going to apply those equations to a specific situation, in this case essentially two nested solenoids. So I've got this inner solenoid here, and then I've got a solenoid wrapped around the outside, and I want to know what the mutual inductance between the two solenoids is. So the B field from a solenoid, if you remember, is mu naught N I over L. So if I'm interested in the mutual inductance, I'm going to say, we'll do it from the perspective of the second coil, what's called N2 here. So we'll say that that is N2 times the flux onto from coil 1 over the current 1. And in that case, it is coil 1 that's producing the magnetic field that is producing the flux over here. So we're going to put 1 subscripts on all of these. So if I rearrange, I'm not going to rearrange yet actually, sorry. The flux can also be found by doing B times A. In this case it would be the integral of B dot dA, but that's just going to give us BA because the magnetic field and the A are parallel to each other. And so if we substitute this in for B, we're going to get mu naught N1 I1 over L times A, so we just throw an A on there. Then I'm going to come back to this expression here. I'll jump down here so I have more room, and I'm going to plug in this guy for my flux here. So I've got N2 over I1 times this big sucker here, 1 I1 A all over L. So the current actually cancels out, which makes sense because the mutual inductance depends on the kind of geometry of the orientation between these two elements, not on what current happens to be passing through at a given instant. It's a constant as long as your physical setup is constant. So this works out to be, we'll put the mu naught out front. The number of loops of each coil matters over L, and then we've got the area on the end here. So you'll be using this one a bit in your homework, so you probably want to jot that guy down. This is for solenoids. Okay. So we have mutual inductance where one element can induce a current in another, but if we have even just a simple circuit, I've got my battery and I've got a coil of wire here. Well, and I guess we should have a switch here or something. So initially the switch is open. As we close the switch, we're going to start to get a current, and as that flows through this coil, I'm going to get a current in a coil, which is going to produce a magnetic field. Well, that changing magnetic field is going to produce an EMF on this element itself. So again, we can say that the flux is going to be proportional to the current flowing through this coil, and usually we write it in terms of the flux through one loop times the number of loops. I don't need subscripts now because there's only one coil to worry about. Oh, sorry, this was proportional to, and then to make it equal we need to add a constant of proportionality. In this case we're going to use an L. Why, I'm not sure, but that is the symbol we use for self-inductance. So that's going to be equal to but flux of B. We also know that the EMF is negative. I probably lost the negative sign in the previous one, didn't I? I do that a lot. It's all right. Okay, so we've got this thing going on. If we solve this guy for flux, we get IL over N, and we substitute that in here. Again, we can pull out the N and the L because they're constant. So we're going to get negative N times di dt. The L was out here, the other N was down here, so those cancel, and we end up with EMF is negative L di dt, where L is known as the self-inductance. It also has units of henries. So henries apply to all types of inductance in general. Now let me jump to an applet and show you a little bit more what's going on with these types of components. They are known as inductors, and they're kind of our third and final fundamental circuit components. We have capacitors, we have resistors, and inductors are kind of the main fundamental components. Alright, so here I have a simple circuit with just a switch, a battery, and a coil of wires. So this is my inductor. I'm not getting a pointer. Oh, there's my pointer. So if I close this switch, normally I would instantly jump to a really high current because there's no resistance in this battery. It assumes no resistance in the wires, and there's no resistance in this coil either. So you would just spike up to an infinite current. But because of the EMF produced in the coil, which will always oppose the other EMF because it's going to oppose changes, it doesn't want the current to increase because that's going to make the magnetic flux increase. So this is going to slow down the increase of our current. Now, since there's no resistance, this thing will keep speeding up forever and ever until things catch fire or whatnot. I won't wait that long, but you can trust me, it just keeps increasing forever. If there's actual resistance, then it doesn't. It would reach some peak current according to Ohm's law. Now, the other interesting thing is if we have some place for this current to go, so let's get kind of a steady state going here. Now if I disconnect the battery, normally all of the currents would instantaneously cease if there's no more voltage source. But essentially this guy, not only does it slow increases, it also slows decreases. So it's going to keep the current going. Just like we saw with Lenz's law, inductors oppose changes in the flux, which in circuits means they oppose changes in the current. So it keeps it going for a while. Alright, back to the presentation. So just kind of reviewing what I just showed you, if the current is increasing, it's going to oppose that increase, so it will create a potential, an EMF, where you essentially have a positive potential and a negative potential on this side. If it's decreasing, it's going to do the opposite to try to keep pushing current in the same direction it was going. See here it's fighting against the current, here it's going with the current. Alright, and now we're going to look at the inductance in a solenoid. A lot of times we don't use self-inductance, we just shorten it to inductance. So once again, we've got the magnetic field from the solenoid, mu0 Ni over L. And we want to find the inductance. Whoa, my eraser's not working, so I'm just going to scratch it out. Okay, so L is going to equal, and I'm going to drop the negative sign. No, I didn't have a negative for this one. I don't know that I solved for L in the previous slide. Well, we had that expression that IL equals N times the flux, so we can rearrange that and get this as our expression for inductance. I should have done that earlier, but we got it now. Alright, so we can go ahead and plug in, similar to what we did earlier, we can get an expression for the flux, which is going to be B times A, where A is the cross-sectional area of our solenoid. And we've got our B field right up here. That mu kind of looks like a W, but whatever. And that times the area, and then we plug this guy in over here. So we get N mu0 N times I A over L. And it works out to be, instead of having the ends we didn't have ends cancel out last time, did we? We had other things cancel out. Anyway, we end up with this expression for the inductance of a solenoid. Let me double check. Did I screw something up? Yes, the I's. I knew something was supposed to cancel out. That's what canceled out last time too, which I mentioned why, because it shouldn't depend on the current. Okay, there we go. Now on to the calculations.